Alright, welcome back everybody. Continuing off with our project, How the Earth Moves, our third group is going to be Joel's groups.
Thank you. Hello everybody, my name is Joel, and these are my roommates, Emmanuel, Ishmael, and Diana. Alright, we're going to be talking about how the Earth moves. So, yeah, Diana.
Okay, so I'm going to be talking about tropical year, also known as solar year. So basically what tropical year is the amount of time it takes Earth to travel around the sun. And this is usually in seasons. So typically we don't have exactly 365 days. It's usually 365 days, and according to tropical year, it's 5 hours, 48 minutes and 45 seconds. And then, so this is basically it's when the vernal equinox, that usually happens around March 20th or the 21st in the northern hemisphere. And in the southern hemisphere, it's usually September 22nd or 23rd. And that's when it starts, so that's when the seasons, the Earth like usually starts their seasons according to the tropical year. But so this is like it's not the same length. So every time the Earth travels 1 year around the sun, it's usually not what is it? It's usually not the same length as the leap year, because leap year has an extra day in February, and the tropical year is usually 20 minutes shorter from a sidereal year, and so that's what that is.
Okay, I will talk about photons. So, photons are basically particles that represent a quantum of light, or any electromagnetic radiation. And basically photons, they maintain a constant motion, which basically makes them massless. So they have no electric charge and rest energy. They are elementary particles despite lacking rest mass. So basically, to get a good understanding about this, all the lights you see in this room, the layer of light that they project are pretty much photons when you look at it in a very, very microscopic lens, which is really visible to the naked eye. And they move in waveforms, represented right here in this corner picture. You can see photons are the little blue dots right there, and the motion that they move in is in the waveform. And the equation that I have right above it is E equals H times F. E representing energy, so if you're ever trying to locate the energy of a photon, you would use this. H representing, I think it's called, Pax constant. Yeah, Pax constant. Pax is the guy who actually came up with the equation to begin with. F would be the frequency of radiation, so it basically would be, in order to find the energy of a photon, you would need Pax constant times the frequency of the radiation. And the radiation that the lights in here project, the energy from them, is very, very weak. That's why we're able to, constantly be under lights. But now if you think about the sun projects a lot more energy because it has way more photons, way more particles to work with. But yeah, something I found really interesting, I'll give you a quick example, is, this is a terrible example, but there's a layer that shoots up of light, and when I did the research, you think that the layer would be just one constant layer, but actually when you really look deep into it, can't really see with the eye, but there's actually gaps in between the layers. which scientists have used before in order to locate certain photons in different types of lights and stuff like that. But yeah, that's basically a little bit, about photons. Thank you.
Hi everybody, how you guys doing? Today I'll be talking about the sun. So obviously the sun is, in our solar system, it has the most mass. The majority of the mass in our solar system comes from the sun. The majority of our energy on Earth comes from the sun. Pretty much without, well, we would probably survive without the sun now, but before in the old days, without the sun, pretty much this was God, pretty much to them. Yeah. So fusion. Fusion is the process of which the sun gets energy, or actually produces energy. Fusion is the process that powers the sun and stars. It is the reaction in which two atoms of hydrogen combine together. So obviously two atoms of hydrogen are going to combine. I believe it is 600 million tons of hydrogen gets burned every second under the sun, which produces energy. This eventually turns into helium. In the process of the mass of the hydrogen is converted into energy. Through this process, energy is created. So if I can give you like an example, you see what I have here? A lighter, right? If I burn the lighter, what's burning? Oil, right? Or not oil, but flammable gas, right? It's the same thing. It's burning fuel pretty much. And once the fuel runs out, it will turn into a red giant, I believe. Once that hydrogen gets over with, it will pretty much shrink, or actually it will expand and turn into a white dwarf, in which we'll probably be dead if we're still on Earth. That's...
Alright everyone, I'm going to present about latitude and longitude Earth. As we all know, our home is if you see right here, latitude is
Breathe, go ahead, breathe. Take a deep breath, let it out. Think about Santa Claus for a second. All right, try again.
All right, the Earth is a vast universe. It's a vast universe.
It's a what?
It's a big universe.
The what is?
The Earth.
The Earth is a big universe?
It's big. I'm trying to.
Compared to what? Try again.
The Earth, right here, is our home.
Yeah, that's
As
true.
far as universe, it's kind of hard to locate. There's a different type of like places in the Earth, and for instance, like if I ask you to locate, like there's a different type of like place in the Earth, right? For instance, if I ask someone here like to locate like San Francisco, the Colorado Bridge in San Francisco, San Diego, it's kind of hard to locate the accurate part, right? But if I give you guys the coordinate, it would be easier to like locate it. So latitude, the polar latitude and longitude form invisible plate on the Earth. Yeah, when you see right here, this line is called the parallel line, which is circles around the Earth from east to west. Imagine this line as a hula hoop that's circling around the Earth. So if you see right here, it's the distance between these two lines. It's like it's the same distance, apart. That's like 69 miles apart, and in the degrees, and 1 degrees is measured in a small particle called minutes, and minute is also divided into like second. If you see right here, the equator, it lays on 0 degrees in between the North Pole and South Pole, and there's several like unique latitude lines. The tropical Cancer, it lays on 23 and a half degrees north, and there's the tropical of Capricorn, which is 23 and a half degrees south. And the surface in between the North Pole and the South Pole, which is going to be like right here, is called tropical, and it's known for its dense jungle, heavy rain, and yeah. And the other one is the Antarctic Circle, which is 66 and a half degrees north, and the other one is Antarctic Circle. It lays on 66 degrees south, and the other one is longitude. Longitude is the circle, the line that runs down from north to south. It's called the meridian. The meridian latitude. And the meridian. It's called the meridian. So the point right here, it's called the prime meridian. The prime meridian, and longitude is, it uses like the same measurement, which is degrees, second, and minute. And unlike latitude, it's equivalent to each other, and yeah.
And yeah,
Thank you.
all right, that's it, right? They're done?
Yes.
One more? Who's next?
Any questions?
Oh.
Yeah, that's it. Any questions,
Is that
guys? Jose?
I'm sorry, Ishmael, you said something like, we could survive without the sun, correct?
Well, yeah. Right now.
Okay, so, seeing that the sun is